In this video we're going to look at the content for exercise 11H, and it's called miscellaneous questions or something like that, but what it's actually trying to teach you is a process called integration by recognition. And we use integration by recognition when we're integrating functions that we don't actually have an integration pattern for. And it always comes in two parts, always. The first part, you're asked to differentiate a function, and then the second part will say hence, or using your answer from part A. It implies that you've got to use your answer from here to find a particular integral. So what we actually do in part A is we find the derivative of a particular function, and that gives us f dash of x. And then in part B, what we do is we actually take this equation up here from part A and write it the other way around, so f dash of x first is equal to, so you can see f dash of x is equal to the derivative of f of x, and we integrate both sides. And then we use algebra on this section here to manipulate the equation on this side so that it looks like the required integral. It's probably easiest to just do it with an example. So let's do an example. So here's an example of an integration by recognition question. So we have part A, find the derivative, and here's our function, and part B, hence find this integral here. So the first thing we're going to do is find the derivative of this particular function here. Now this particular function is a composite function, so we've got an inner function and an outer function. So when we find the derivative, we're going to find the derivative of the inner and then multiply it by the derivative of the outer function. So when we do that, we get the derivative of the inner function, which is 2x, multiplied by the derivative of the outer function, so we'd had a power of a half, so the half comes out the front and drops by 1 to become minus a half. So our derivative function, the 2's cancel, and you're left with x over the square root of x squared plus 2, which kind of looks a little bit like what we've been asked to integrate. And so what we do is in part A, what we've done is we have found, and here's the pattern that I used before, the derivative of this particular function is equal to this particular function here. And for part B, what we're going to do is we are going to integrate both sides, and then we're going to swap the sides around. Okay, so we're going to integrate both sides and we're going to swap the sides around. So you can see here that this is actually the right-hand side of this equation, and that the left-hand side is now on the right-hand side. So I've swapped the sides around. But otherwise, this yellow equation is exactly this equation here. So now I'm going to go ahead and I'm going to integrate the right-hand side. So the integral of the derivative of this function here just spits this function out with a plus c. And now I've got the start of an equation, and I'm going to continue through. I have to make this integral here look like the integral that we had at the top up here. So we're looking for this integral with a 3x here. So I guess you can already see what I'm going to do. So what I am going to do is that I need to have 3x on the top. So I'm going to multiply both sides of that equation by 3. So multiply both of the whole of those sides of the equation by 3. And then what you can do is bring this common factor of 3 back into that integral, and now it looks exactly what it's meant to look like. We can multiply our 3 through the terms we've got here. So 3 times this square root gives you 3 times the square root, and 3 times a constant is, of course, just a constant. And so we've found the integral that we were asked for without being able to use an integration pattern for it. So the last question I want to show you is a VCAR question, and it's got definite integrals in it, not infinite integrals. So let's have a look at that one. Okay, here we go. So it's from the 2010 paper, exam 1. Part of the graph of the function f where positive real values, so notice there's a hole here, positive real values map to reals for the function f of x is equal to x log e to the x is shown. Part of the graph. Find the derivative of x squared log e to the x. And then part B, use your answer to part A. So it doesn't say hence, but it does say use your answer to part A to find the shaded region. So the shaded region is going to be the integral from 1 to 3 of that particular function. So it is asking us to find an integral. And then it wants the integral in a specific form, in the form of a log e to the b, log to the base e of b plus c. And it also specifies that a, b and c are non-zero constants. So you're going to have to find an a, a b and a c. So our first job is to find the derivative of x squared log e to the x. And because this is in exam 1, we need to do it by hand. So what we've got there is a product of two functions, and so we are going to use the product rule. Now your formula sheet has the product rule on it. You'll have it in exam 1 if you forget. So away you go, you can work through. You'll need to find du dx and dv dx, and I've already done it there for you, and then put it together using our product rule. Now I want you to notice that I have written here not dy dx for my product rule. So I've let u equal this and v equal this, and I've got du dx and dv dx written here. But when I actually write the derivative, the original question has f of x. So my derivative has to be f dashed of x. Okay, so put it all together, tidy it up, and you can see that it's starting to look a little bit like our equation of our original function up here. So what we're going to do is we are going to integrate both sides of that equation. So there's our area formula. So I should say there's our area formula. You can see that this looks a little bit like this. Here it is sitting right here. So we're going to integrate both sides of our formula from before. So here's our formula. The derivative of this function is equal to this. So we're going to put this on this side, this on the other side, and we're going to integrate the two. And because we've got definite integrals here, what we're actually going to be working out is this integral with some endpoints on it, with a 1 and a 3 here, and a 1 and a 3 here. So what I'm going to do, I'm going to split this integral into two integrals so I can get this one by itself. And so to do that, I subtract this first integral from both sides, and I take the common factor of 2 out of the front. You can see it's starting to look more like the area up here. And then I work out all of this stuff over here. So I'm going to integrate my derivative here. So I've got the integral of a derivative. So that will just give me the function out as my antiderivative. So this comes into here, and I evaluate it at 3 and 1, and then I evaluate this integral over here for 3 and 1 as well. When I do that, I get this blue section here and this red section here. That should have a little red line underneath. And I've also taken the 2 from out the front here, multiplied both sides by a half, so that now this is the integral for the area. And I've dropped my dx off there. I should fix that up. There we go, that's better. And now just tidy up this side. So let's go through here. So we substitute the 3 and we get 9 log to the base e of 3. Substitute in the 1, we get 1 log to the base e of 1. Substitute in the 3 here, we'll get 9 on 2. Substitute in the 1 and we'll get a half. Log to the base e of 1 is 0, so this just simplifies to 9 log to the base e of 3. Take away 9 over 2 minus 1 over 2 is 8 over 2, so we end up with 9 log to the base e of 3 minus 4. If we then multiply through by that half, we get 9 on 2 log to the base e of 3 minus 2, and that is in the form that's required by the question at the start. So for finding integration by recognition, the absolute key point is to take your relationship here, integrate both sides, and then write them in swapped sides configuration. Then manipulate to get the integral that you want. It takes a bit of practice, so try on a few questions.